Page 84. Okay, so saturated solution. It is a solution that contains the maximum amount of solutes. So basically, when you dissolve something and you put in so much solute that it will not dissolve anymore. How did we know that the calcium hydroxide solution was saturated? When we made our solution on Wednesday last week? Wednesday, yes. Yeah, there were still little particles in there. We stirred it, we heated it, and still there were little particles in there. Okay, so that is a saturated solution. How can you make a saturated solution? Well, basically, you just keep adding solute and stirring until what? Until it's all dissolved? Until no more dissolves, until you have some solid left over. Okay, so you add, you stir, you add, you stir, you add, you stir, and then you're like, oh, I'm still stirring and this won't go away. This solid is still here. All right. Then, if you want to, you can do like we did in our lab and you can filter it so you can get a clear solution without any solid suspended. So you'll have a saturated solution without the solid, okay? WO for without. What kind of compound is calcium hydroxide? What are the two kinds of compounds? Two kinds of compounds. Covalent and ionic. Which type is calcium hydroxide?
Ionic.
Ionic, how do you know?
Metal.
We got a metal here. Anytime you have a metal, you know that it is ionic. Which means it's made of ions. We have our cation, we have our anion. Moving right along. Oh, why do we need the 2 in CaO? CaOH2. Why do we need that 2? So we can have a neutral compound. Now, in addition to that, you guys should be like, oh my God, Miss Spence, what have you done?
Brackets.
I need my brackets, yeah? And the reason this gives us a neutral compound, calcium is in group 2. So what is its charge? 2 plus. Hydroxide, where do you look for its charge? You look on your pink sheet. Okay, if you don't already know it, perhaps by this point you know hydroxide is -1, or, over time you will. Okay, so there we go. So we have a neutral compound. The positive has to be equal to the negative. All compounds have to be neutral by definition. If it has a charge, it is not a compound. It's an ion. Okay. What structure does it make? It makes a crystal lattice. And one thing I'd like you to notice here is that we have our negative ions And we have our positive ions. Why are the negatives bigger than the positives? Have a little chat about that.
Yeah, I know.
All right, what do you think? Ideas. Throw them out there. Yes?
The anions gain more electrons.
The anion gains an electron, yes. And what do electrons do to one another?
They repel.
They repel. So if they're like here and all of a sudden you put another one in, what are they going to do? They'll be like, I must get away from these nasty negative things. Okay? So that's why our negative ions, they gain electrons, and we have extra electron repulsion. So the anions get bigger than their parent neutral atoms. What about the positive ions? Yeah, what about them? Why are they smaller? They lose electrons. Where do they lose electrons from? From which shell?
Valence shells.
The valence shell. Are there any electrons left in the valence shell after they lose their electrons? No. So you go from having possibly maybe 5 occupied shells to having only 4. 5, 4. So it's actually quite dramatic. It's like 5, 4, 5, 4. Okay, and you can see on the next page, I have a little picture of this. Okay, we have calcium, which is in row 1, 2, 3. It's in row 4, so it has how many shells? If you're in row 4, you have 4 shells. And it's in group 2, so how many valence electrons? 2. So that let me draw a really quick and ugly, calcium ion, calcium atom Bohr model. And you can see we are losing our 2 electrons. Okay, and what are we left with after we are done? Only 1, 2, 3 valence shell, occupied shells, and you can see that just makes it a lot smaller. Because I did this in my regular class last year, we were like, how many protons, how many electrons, blah, blah, blah. Anyway, we don't need to do that. Yes? We're good. Okay. So cations are smaller because we have fewer occupied electron shells. Okay. Calcium hydroxide. Let's see what we got here. Metal plus a polyatomic ion, therefore it is an ionic compound. What do they look like? They look like crystal lattices. So I have drawn a crystal lattice here. And because we're going to have to draw a lot of these, I don't want to draw all those positives and negatives. So I have shrunk it. Shrunken. Yes? So I'm just making it smaller and more manageable to draw. So this is also an ionic crystal lattice. This is a mini crystal lattice. And CaOH2 is a powder. Yes? And so each of those grains of powder is a small crystal lattice. Okay? So this is a grain of powder. It's a mini crystal lattice. Okay. So here's our solid. And we dump it in the water. And right at the moment when it goes in, what do we have in the water? We have all kinds of little small crystal lattices. Most of those solid particles stay intact and they just float around. Eventually, what will those solid particles do if you let it sit? They will settle. Yes? And you probably saw that happening. If you weren't stirring it, they would settle out a little bit. And then if you let it set overnight, it would probably settle quite a bit. All right, so here are our small crystal lattices. Those are our grains of solid. And it appears cloudy. And the reason that it appears cloudy is because light reflects off the solid. So if you have solid, it will be cloudy. If it appears cloudy, you have solid. And I'm going to draw a little flashlight up here. Okay, so we got our little flashlight. And now we're going to see a light beam shine into the water. And what does it do? It goes bonk. And what happens when it bumps into a solid particle? It reflects and bounces. Okay? So all the light coming out of here, some of it goes through, right? Which is why you do see some light coming through, unless there's like too many solid particles. But a lot of the light is going to like hit little particles and get scattered. So now, in other words, these little crystal lattices are suspended. So what type of substance do we have? We have a? Well, it's saturated, but also if we have these solid particles suspended in solution, we have a suspension. Yes. Okay. We have a heterogeneous mixture. And in particular, a suspension. That's a terrible break in the thing, but anyway, that's okay. So a heterogeneous mixture means you have clumps of different materials in different areas. The clumps might be invisible to the naked eye. So if you look at it, you might not be able to see them, okay, if they're small enough. But if you put it under a microscope, you would be like, oh, there it is. Yeah, you would actually see little clumps. Okay, so the clumps might be invisible to the naked eye, but you will be able to see them under a microscope. Is good? Okay. All right, so now here's our little undissolved mini crystal lattice. And you can see its size. Now water, here's a little water molecule here. You can see that it is much smaller than the mini crystal lattice. That one little red dot represents a water molecule. Now, on the previous page, we hadn't looked at any of it dissolving yet. We had just looked at them being the solid little bits being suspended. Now we're going to look, and we're going to look at some of it dissolving. So these, when an ionic compound dissolves, what do the ions do? They separate from one another. Do you guys remember what that's called? When the ions separate? Dissociation. So some of them separate, and the ions float separately. So in the beaker, we have some individual calcium ions and hydroxide ions. And now we've drawn the dissociated stuff. We've drawn the little undissolved solid. Now we're going to put that all together because now we have a suspension, but we also have the solution because some of it is dissolved and some of it is not dissolved. The mini crystal lattices are really easy to see because they are not dissolved. They're our little squares. Yes? Now, our water molecules I've drawn as little red dots. Okay, those are our water molecules. Now, in theory, there should be way more little red dots because water is it's not the solute, it is the solvent. And so it would be just like blanketing the whole thing, right? The whole thing is basically just water, but that would make it impossible to see, right? So now what do the little blue dots represent? The hydroxide ion and the calcium ion. Now, what do you notice about the relative size of the ions in the water compared to the mini crystal lattices? What can we say about the relative size of ions and water versus the mini crystal lattices? Have a chat with your neighbor. What can you say about the relative sizes of the water and the ions versus the mini crystal lattices? Anyone want to tell me? Yes. Yeah, these guys are smaller and these guys are bigger. And that's going to be important because when we go to pour it through the filter has little teeny tiny holes in it, little pores in the filter paper. Yes? Because it's made of paper and the fibers are like crisscross each other. So you can be like, oh, look, there's a little hole in there. Yes? But not a big hole. Okay? So if I have my mini crystal lattice, okay? And if the hole in the filter paper is this big, right? If I rip off one of these ions, will that fit through the hole? Yes. Okay? Water molecule is about the same size as one of the ions. Will it fit through the hole? Yes. What about the mini crystal lattice? No. Okay? And so that's what's happening here. The calcium hydroxide solid particles are too big to fit through the filter paper pores. And that's why the mini crystal lattices stay behind. But what comes through? The water and the ions. So water fits through the filter paper pores. Calcium and the hydroxide also fit through the holes. And so they drip through. So once it has dripped through, what do we call that thing that has been dripped through? That is called the filtrate. And do you remember, was the filtrate clear or was it cloudy?
Clear.
It was clear. And it is clear. See if you can tell your partner why it is clear now. The particles are too small to scatter light. Yes? So maybe I have my flashlight again. And what happens when I turn on the flashlight? The light just goes straight through. Okay? And it has to do with the wavelength of light. Visible light is like hundreds of nanometers. The wavelength. You guys know that symbol for wavelength? It kind of looks like a wave, doesn't it? Like a little, right? Anyway, that's lambda. Okay, Greek letter lambda, and it stands for wavelength. And the wavelength for visible light is in the neighborhood of like 400 to 800 nanometers. I feel like somewhere in there. Okay? Hundreds of nanometers. And these little particles, they are about 1 nanometer or less. Okay? So, 400 to 700, I think, nanometers. And the ions themselves are like 1 nanometer or less. So that's why they're not big enough to scatter the light, because the wavelength is so much bigger than the particles. But if you have a suspension, the particles are bigger than 1 micrometer, which is 1,000 nanometers, which is big enough to scatter the light because it's bigger than the wavelength of the light. You don't need to know that. I barely understand that. I don't even know what I just said. So forget I said anything, okay? Basically, if you shine the flashlight and the particles are too small, light does not scatter. If you shine the light and the particles are big enough, the light scatters, cloudy. If the light doesn't scatter, clear. Now, that doesn't mean that there can't be a color to your solution. For example, copper 2+ ions are blue and they do not scatter light. So if you look at it, it looks clear, like the light passes straight through it. There's no cloudiness, but it is blue. Okay? So solutions are clear. They might be colorless or they might be colored. And the reason I make that distinction is because in regular life, we tend to say, if you look at water, you're like, oh, it's clear, right? And then you look at, the Gatorade and you're like, oh, it's blue, right? But the Gatorade is both blue and clear, yes? Whereas the water is clear and colorless. So just be aware that in chemistry, we specifically use the word clear to mean transparent, okay? It doesn't just mean without color. If you want to say without color, you say colorless, okay? All right. I don't know how useful this page is. Basically, I was just like, this is more for regular 11. And I made a Venn diagram showing solutions and homogeneous mixtures. And you can see that they are the same. Do you see the homogeneous mixture is the red circle? And the solution is the black circle. And they are the same. They actually literally mean the same thing. Okay? So you could even have a solution of metals. So for example, steel is a solution. 18-karat gold is a solution. So when I said before that all solutions are clear, I lied to you. I should have said that all aqueous solutions are clear. Okay, so maybe I need to go back and change that. All, where was it? Solutions, aqueous solutions are always clear. Because if you have a solid in solid solution, you know, you melt the metals, you mix them together until they're mixed thoroughly, they're homogeneous, and then you solidify it again, that is still called a solution, but obviously it's not see-through. You know, you don't pick up your knife and go, ooh, I can see through that. No, okay? Right? You can also have a gas in gas solution, right? That's going to be see-through because like the air. Yeah? It is a solution of oxygen and carbon dioxide and argon and some other things in the main component. Do you guys know the main component of air? What's the main gas? It's not oxygen, it's not carbon dioxide, it's nitrogen. Yeah, okay? Main component is nitrogen and all the other gases are dissolved in it. They're just mixed thoroughly, okay? Okay, so a solution and a homogeneous mixture are the same. Oh yeah, and so now we were talking about what happened when you blew into the lime water. It started clear, and then it turned cloudy. If it turned cloudy, do we still have just a solution? No, now we have a suspension. Suspensions are always cloudy. And that's a type of heterogeneous mixture. I don't think that you need this little Venn diagram for this one because it's just kind of stupid. It just says all heterogeneous mixtures are called mechanical mixtures. That's more of a junior high school term, mechanical mixture, right? I don't think we use it very often. And all suspensions are heterogeneous mixtures. That's all that's saying. But it looks like a donut. Donut. Okay. Anyway, you can just ignore that. It's fine. Now, one of the questions asks you to draw I think it's number 7, asks you to draw a diagram of a saturated solution of calcium hydroxide. And what you should be drawing for that is you should be drawing number 1, the crystal lattice, right? Because there should always be some solid left over or undissolved in a saturated solution. Yes? Now, should you in theory be drawing lots of little mini crystal lattices? Yes, but do we have time in our lives to do that? No, so we can just draw one crystal lattice. Second thing to notice here is that when we have our dissociation equation, that's what this is, our dissociation equation, there is a ratio between particles here. What is the ratio between the calcium and the hydroxide? Yes. There's 2 hydroxides for every 1 calcium. You can also see it in the formula over here. There's 2 hydroxides for every 1 calcium. So when you draw your saturated solution and you draw some calcium ions and you draw some hydroxide ions, whoops, there we go. The ratio should be 2 to 1, okay? Or 1 to 2, depending on how you want to express it. There's 1 calcium for every 2 hydroxide ions. So you can see in this particular diagram, I've got 2 calcium. How many hydroxides do I need for that? I need 4, right? Twice as many. You'll probably also notice that in our crystal lattice, I have not drawn a 2-to-1 ratio. Yeah? And that's because it is too hard to draw a 2-to-1 ratio. Like, I can do it if I'm cutting and pasting circles, but if I actually have to like draw it by hand, I am not talented enough to do that. Okay? Just not talented enough. So just go with it. Yes? Okay? And so we simplify our crystal lattice. We always draw it as 1-to-1, even if it's a 2-to-1, because it's just simpler. Okay? Okay. Now, that's it for like this little doodad. This is what I went over with my classes last year. Do you have any other questions about the lab? Anything you'd like to know? Anything you'd like to go over before you're ready to hand it in? And you can either hand it in today if you're done today or tomorrow if you need a little time to fix things up. Any other questions? No? No questions? You guys are good? All right, excellent. So that being said, I think let's just talk about what chemistry happened during the dissolving versus the blowing bubbles and seeing that cloudiness form, okay? Why are we not adding a page? Okay, add a page. There we go. Okay. Pen stopped working. That's exciting. Let's see if this pen works. Yes, it does. Okay, good. All right. So the dissolving / dissociation is this a chemical or a physical process? So what we're going to do is we're going to think about this for a moment. I'm going to write down the equation. We've got CaOH2 solid becomes Ca2 plus aqueous plus 2OH minus aqueous. Yeah? So if I had to draw this, I'd have Ca2 plus, and I'd have an OH and an OH. Just one formula unit, okay? And if I had to draw this over on the right-hand side, I would have Ca2 plus, and I would have an OH, and I would have an OH. So I am starting with Ca2 plus and OH minus ions. What am I finishing with? I'll let you write that down and then think about it. So I started with calcium ions and hydroxide ions. What am I finishing with? Calcium and hydroxide ions. Have we created anything new? No. There's no new substance. So this is just a change of state. It has changed from solid to aqueous, and therefore it is a physical change. So we go from solid to aqueous. So that is a physical process. Now, on an AP exam, no one's going to ask you whether dissolving is a chemical or physical process. Okay? So you don't actually have to worry about it that much. And in fact, dissolving is almost in a gray area where it's kind of almost one and almost the other. But in general, we consider it a physical process. And the fact that we would name the two substances the same name, we would say that this over here is calcium hydroxide solid. And over on the right, it is calcium hydroxide aqueous. So it's the same substance before and after. Yeah? Now, what about when you blew the bubbles into the calcium hydroxide solution? Did you get a new substance? And if you did, how could you tell? Yeah?
There was a formation of a new solid.
Yeah, there's a formation of a new solid, right? It was not cloudy and now it is cloudy. We did not have a solid, now we have a solid, okay? Now we're going to look at what's in the beaker and figure out what that new solid is, okay? What did we blow into the water or into the lime water?
CO2.
Carbon dioxide. Okay. And remember, what is lime water? It's just a CaOH2 solution, okay? It's called that because Calcium hydroxide is also known as lime. That's its common name. Okay, if you like find it in nature, you'd be like, oh, look, some lime, which doesn't mean that it's that sour fruit that's green. No, different kind of lime. Okay. Sometimes, have you ever heard of like putting lime in your garden? Yeah. So if your soil is too acidic, you might put down some lime, and that you're putting down some calcium hydroxide, and it's going to make your soil a little more basic if it's too acidic. Okay. So we take CO2 and we are putting it into water. And if we were to cram all of those atoms together into one formula, what would we get? Take all of those atoms and smush them together. We're going to put the H first. And what do we get? H, 2. How many C's? 1 C. How many O's? 3. H2CO3. I would like you to name that compound, please. You can use your pink sheet, okay? Do you need a pink sheet?
Carbonic acid.
Yeah, you could call it hydrogen carbonate, but it would be better to call it, because we know it's got that H. What kind of substance is it? It is an acid. And it is based off the CO3 2- ion, which is carbonate. And what if we have an 8 ion? What is the mnemonic device, the memory device that we use to remember how to name the acid? I ate something icky. Okay, so what that means is we're going to take carbonate and we're going to turn it into carbonic acid. So we have made carbonic acid. Yes? Pardon me?
We started with the base.
And now we're adding an acid. We still have the base. Okay, so this is step 1. Step 2, it reacted with the water part of the lime water. We still haven't dealt with the lime part of the lime water. Okay. Step 2, now in our beaker, H2CO3, which is aqueous. And what's the other thing that's in our lime water? The lime part? Calcium hydroxide, yeah. My goodness, those two things together, hey? Can those things react together?
Yes.
Yes, because we have, what kind of compound is this one? The red one? Acid. And we have a base. What type of reaction will that be? Ooh, actually, let's list all our types of reactions. Tell your partner, what are all the types of reactions? I think there's 6. Yeah? Combustion?
Neutralization.
Neutralization. Yes, double replacement. Single replacement. Something with a D. Yep. Decomposition. The opposite of decomposition is synthesis. Yes. So those are our 6 types of reaction. What type do we have with our acid and our base?
Neutralization.
That is neutralization. Ooh, by the way, our other reaction in step 1, what type of reaction is that? Synthesis. It is a more complicated synthesis than like straightforward element plus element gives compound. And if you were in regular 11, you would never have to be able to predict this. Well, actually you do in grade 12, but you should be able to predict the products of a non-metal oxide plus water by grade 12. Okay? You don't need to this year, but in grade 12, we look deeply into acids and bases. And when you have a non-metal oxide plus water, you get an acid. And usually you just cram them all into one formula. Okay? And don't worry, we'll learn about those in grade 12. I'm just mentioning it now so you're like, oh, I've seen this before. Okay? And interestingly, if you have a metal oxide with water, you get a base. But we'll look at that next year. All right, so we have an acid and a base. Do you guys know how to predict the products of this reaction? Yeah? Go ahead, do it. Predict the products. What do we get? And if you don't know, that's okay. Don't worry, I'll go through it with you. There's a whole unit on reactions. Yes?
Calcium carbonate.
We get calcium carbonate, CaCO3,
Water.
and water. Yes. Okay, now if you saw that and you're like, yes, excellent, I know that, that's wonderful. I'm going to give you just a little quick preview of a predicting product technique that works for double replacement and for neutralization. And it makes it really, really easy to predict the products. Basically, what you do is you write your ions and you say, I've got H and CO3. I've got H plus and I've got CO3, 2 minus. In my second compound, I have Ca2 plus and I have OH minus. So I write out all the ions that I have in the order that I see them in the equation. And then what I do is I combine my outside ions, so the ones that are on the outside, so that means that the H plus will get together with the OH minus. I only need one of each, right? So I end up with HOH, which is the same as H2O. So I go forwards when I combine the outside ions, and then I combine my inside ions, and I go backwards when I do the inside ions. That means I'm going to end up with my cation first. Okay, so I've got the calcium, 2 plus, and carbonate is 2 minus, so I just need one of H, so I end up with CaCO3.
That's in salt.
And that's the salt. Yes. So you have your acid plus a base gives you salt plus water. And that's your neutralization. Yeah? Acid plus base gives salt plus water. And I will let you in on a little secret. If you ever have trouble balancing a neutralization reaction, if you're ever like, I don't know how to balance it, like you might have no problem balancing this one. But I'm just going to show you this just for argument's sake. If I write my H and my OH as separate things, and I treat the OH as a different unit than the H, and I balance the OHs and I balance the H's separately, what I can do is I can say, okay, normally what I will do is I will start with my salt and make sure everything is balanced within the salt. So is my calcium balanced? Yes. Is my carbonate balanced? Yes. Then I go on and I pick hydrogen or hydroxide. It doesn't matter which one. And I say, is my hydrogen balanced? I have 2 hydrogens over here. That means I need to have 2 hydrogens over here. And I ignore the hydrogen in the hydroxide because I'm treating it separately. Then I say, how many hydroxides do I need? Quite frankly, if I balance the hydrogens, the hydroxides will also be balanced. Okay? And I go, oh, I need 2 hydroxides. Well, isn't it good that I happen to have 2 hydroxides? And it becomes that simple to balance. Okay? So if you ever have trouble balancing those, and the other thing to remember is that the number of hydrogens and the number of hydroxides and the number of waters will always be the same, because you have to have 1 hydrogen for every 1 water, and you have to have 1 hydroxide for every 1 water. So if you have 2 hydrogens, you must end up with 2 waters. Is good? Okay. Now, is this a chemical process or a physical process? Chemical change. Okay, we have our new thing there. And the water is a liquid, so we have formed a new substance. We formed water. And what state would the calcium carbonate be? It would be we blew bubbles and it turned cloudy. It would be a solid. And the reason it's a solid is because calcium carbonate has a very low solubility. And what does it mean if it has a low solubility? That means it dissolves poorly. Okay? And so, again, the fact that we made that new solid, that counts as a new substance because we've recombined the ions with different partners. And I think this is all I did with my other class. And it's 10 too. What did I assign for homework? Let's see.
So,
Yes.
what was the last type of reaction?
So we have combustion, neutralization, double replacement, single replacement, decomposition, and synthesis.
Can't spell that. Synthesis.
Synthesis. S-Y-N, and then the, and then like sister, sis. What temperature is it? It's 27 degrees in here. That's ridiculous. Poor Mr. Ronsley. I'm always sending him like updates about what the temperature's like up here because they're busy sorting out like the things. But if you don't send him the data, he doesn't know, right? And I'm always like, hello, me again. It's 27 degrees today. Scientist, checking the thermometer. Sorry. Anyway, that's all we got through with the other block because they had a couple more questions about the lab. What did we give them for homework? Ba-da-ba-ba-ba. Where did it go? Oh. I think, okay, let me see. Moles. Read the examples on page 81 and do page 85, and that's in your mole book. Okay?
So like that's the thing.
It's related to that. This one's about finding molar volume. It's what you were doing this morning, Jade. So you don't have to do it. Yes. We'll talk more about molar volume tomorrow just to make sure everyone's on the same page with it. But oh, did you all do the questions on like the page 90s over the weekend in the mole book? Because there were a couple people in my other block who didn't. So if you didn't do it by any chance, then that would also be your homework for tonight.
Oh, right.
How we will go over it all tomorrow. Okay. So all of that stuff, I know you're doing a lot on your own right now. We'll go over all of it tomorrow.
Okay.
Yeah.
This one.
Yes.
We have
Yeah, if you are done with your lab, you can hand it into the inbox right now. If you're not done with your lab, you can hand it in tomorrow. That's fine. Paper, yeah, I don't need anything else.
Are you gonna have any of this?
Yeah. Oh, and yes, you get your quizzes back. Yes, yes, yes. Thank you for reminding me.
No. I don't remember where to have it.
Just right here.
Here? Oh. Stop recording. There we go.